Hello and welcome back to the EuroSat channel. We are here to learn together the cutting-edge geospatial science and data analysis techniques. Today, we are going to explain the data preparation steps for land cover and land use classification using deep learning algorithms. Join us on this journey. In this tutorial, we will explore the EuroSat benchmark dataset, a powerful resource for land cover and land use classification. This task holds immense significance in various fields such as environmental monitoring, urban planning, and agriculture. Accurate classification of land cover allows us to monitor changes in the environment, plan sustainable urban development, and optimize agricultural practices. The EuroSat dataset, derived from Sentinel-2 satellite imagery, provides a unique opportunity to delve into the applications of machine learning in addressing real-world challenges related to land use and land cover. The dataset comprises 27,000 image patches across 10 classes, including industrial buildings, residential buildings, annual crops, permanent crops, rivers, sea and lakes, herbaceous vegetation, highways, pastures, and forests. You can access the EuroSat dataset using the link provided in the description. If you know of any other free available datasets for land cover classification or have specific ones in mind, we'd love to hear from you. Drop your recommendations in the comments below, and let's dive into the world of geospatial data together. Now, let's dive into the practical steps. To begin, we need to upload our dataset to Google Drive. In this image, you'll notice that image patches for each class are organized within folders named after their respective classes. Now, create two folders, named Data and Codes in your Google Drive, and then drag the dataset folders into the Data folder on your Google Drive. Once you've successfully uploaded these folders, you'll see a confirmation message in your Google Colab. Next, navigate to the Codes folder, where we'll create a Colab notebook. Simply right-click, and you're ready to proceed with coding. The next step should be connecting Google Drive to Colab. Locate and click on the Files icon and click on the Mount Drive option. A subsequent box will emerge, presenting the Connect to Google Drive button. Click on this button and select your Gmail account to establish the connection with Google Drive. Now that you've established a connection between Colab and Drive, the next step is to optimize your runtime environment. Click on the Runtime menu and select the Change Runtime option. In the new window, choose the GPU option to leverage the power of graphics processing for your deep learning tasks, and then click on the Save button. Now everything is ready to run our codes. Let's dive into the codes. In the first section, we import essential libraries for our tasks, including GDAL for raster data handling, NumPy for working with matrices, and OS for interacting with the operating system. In the next section, the variable folders underscore path is set to the path of the main folder containing subfolders representing different classes. The os.lister function is then used to obtain a list of class names from the specified main folder. An empty dictionary, dict_class, is initialized to store the mapping between class names and their corresponding numerical labels. The subsequent loop iterates through each class, assigning a numerical label starting from 1 and updating the dictionary accordingly. After the loop, the resulting dictionary is displayed, providing a clear mapping between class names and their assigned numerical labels. Next, several crucial parameters for data preparation in the land cover classification task are defined. The variable number underscore classes is set to 10, indicating the total number of classes in the dataset. Patch underscore numbers is specified as 1000, representing the desired number of image patches. In this tutorial, we utilized 1000 random image patches from the pool of 27,000 available in the EuroSat dataset. The variable patch underscore size is defined as 64, indicating the dimensions of each square image patch. Additionally, the bands variable is set to 13, representing the number of spectral bands in the satellite imagery. Two arrays, X and Y, are initialized with zeros using NumPy. The array X is designed to store the input images with dimensions corresponding to the specified patch size and bands, while the array Y is intended for storing the corresponding labels using one-hot encoding, considering the number of classes. In the next section of the notebook, a variable named counter is initialized to keep track of the total number of image patches processed. The script iterates through each class in the dataset, obtaining a list of images for each class. For each image in the current class, it uses GDAL to read the image as a raster array and creates an empty array, new_image, to store the reshaped image with the desired patch size and number of spectral bands. The script then iterates through each spectral band in the original image, copying the corresponding band to the new image array. The reshaped image is stored in the X array at the position indicated by the counter. The class label for the current image is determined using the dict_class mapping, and the corresponding entry in the Y array is updated to 1. The counter is increment, and this process continues until all images in each class are processed. This code prepares the dataset by reshaping and organizing image patches with their corresponding class labels for subsequent use in a deep learning model. In the next section, the script prints the shapes of the X and Y arrays. Then, this section of the script focuses on preparing the dataset for training and validation by shuffling the indices and splitting the data into training and validation sets. First, an array of indices ranging from 0 to the total number of patches is created using the np.arrange function. These indices are then shuffled randomly to introduce randomness in the split. The script proceeds to determine the index for the split, allocating 90% of the data for training and the remaining 10% for validation. Using these indices, it extracts corresponding patches from the original X and Y arrays, creating the final training, X_train and Y_train, and validation, X_val and Y_val sets. Finally, the shapes of these sets are printed for verification, allowing users to confirm that the data has been correctly divided and is ready for use in training the deep learning model. Thank you for watching this video. If you have any questions or need further support, please leave a comment below. Don't forget to like this video and subscribe to our channel to stay updated with future tutorials. Also, you can find the code examples on our GitHub page. Stay curious and we'll see you in the next video.